So you are welcome back to my channel, and in this video we are going to be sneaking in a moment into our simply supported being. That is, if we have a moment among the list of what we are solving, how are we going to deal with it? So that is how we know. So now I mentioned that in simply supported being, the reactions are the first thing that we are going to look for. Reaction at A and our reaction at B. So now our reaction at B, RB times total length, which is times 4, will be equal to the bending moment of the bending moment of the span, that is from A side. So here we will have 20 times 1.5 square all over 2, and here plus this is a moment on its own, so it will be 30. Then this one here, point load, which is 20 times the distance here, which is 20 times 3. So if we add them all up together, we have 10 times 1.5 square plus 10 times 1.5 square plus 30 plus 60, that is equals to 22.5 plus plus 90, which is equals to 110 112.5. That is RB times 4. So divide both side by 4, we will have our RB to be equal to 112.5 divided by 4. And if we divide 112.5 by 4, we are going to get 21.88 kilonewton. So we have our reaction at B to be equal to 21.88 kilo. We have our reaction 20. So if we divide 112.5 by 4, we are supposed to get 28.12. We are supposed to get 28.12. So our reaction at B is 28.12 kilonewton. So now that is our reaction from our reaction for B. So getting our reaction for A, we know that RB plus RA is equals to the total forces on the beam. So we have the force here, which is 20 times 1.5, then plus the force here, which is the force here, which is 20. Then there's no other force because this is a moment, this is not a force. So if we add it together, 20 times 1.5, that is equals to 30. Then here we have plus 20. So and RB here is equals to 28.12. So if we bring it here to be minus, so we have our RA equals to 30 plus 20, 50 minus RB. And RB is 28.12, so that is minus 28.12. So if we do RA minus 50 minus 28.12, we have our RA to be equals to 21.88 kilonewton. So our RA is equals to 21.88 kilonewton. So now we have successfully gotten our reaction at both edges of the simply supported beam. So that's our reaction. Now we move on to solving, starting with shearing forces. So now the shearing force at B will be equals to the reaction at B, which is 28.12 kilonewton. And the shearing force at C here will be equals to 28.12 minus this 20 here, that is minus 20. So it will now be equals to 8.12 kilonewton. That will be the shearing force at C. The shearing force at D, because this is a moment, it does not count as a force, so it is going to keep continuing in a straight line form till it gets to E before it starts experiencing another type of change. So our shearing force at Our shearing force at E here, our shearing force at E would be equals to the same thing that we have there, which is still 28.12 minus 20, which is going to give us 8.12 kilonewton, because it is still in a straight line up to here. But now our shearing force at A, our shearing force at A now will be the reaction at A, which is 21.88 kilo Newton. But now if we look at this, we have minus 21.88, it will be in negative form. So now if we look at this, we have minus 21.88 kilonewton as this place, and we have 8, we have positive and negative here. That means there must be a point in between here and here where where the shearing force is equal to 0. And we remember that the in we remember that when while solving simply supported beam, we always have to look for the point whereby shearing force is equal to 0, and most of the time it is the point whereby the bending moment is usually max. That is, if not for the moment in which we add here, it would most likely be the point whereby the bending moment is usually max. So now let us find for the point. So now if we are doing the shearing force at any point x, distance x from this side, that is, we have any distance x from this side, we use finding for the shearing force from here to here, and that shearing force must be equals to 0. So we do our shearing force, our shearing force is equals to, here we have RB, which is 28.12 minus this, which is minus 20. Then we also have the shearing force from this side, which is equals to minus 20 times x. That is the force here times the distance. That is the shearing force of the UTL here. So if we have this equals to 0, we are going to have 28.12 minus 20, that is 8. We have 8 is equals to 20x. If we divide both sides by 20, we will, this is no 8.12. 8.12, 20 cancel 20. If we do 8.12 divided by 20, we are supposed to have x equals to something like 0.406 meter. We are going to have x equals to 0.4. So write s of the shearing force, s of f at 0, x is equals to 0.406 meter. So we have gotten the shearing force at that point. We'll be able to calculate the bending moment when we get here. So now moving on to the bending moment. The bending moment now at point B, here, we know that it's going to be 0. So our bending moment at B is equal to 0. Then our bending moment at C will be equals to RB times the distance here, and our RB is RB is 28.12, so we have 28.12, 28.12 times the distance, which is 1, that is times 1, which will give us 28.12 kilonewton meter as the unit. So then at D, now our bending moment at D, we are going to have two faces. We can name, one is going to be the face whereby there is no moment, and the other one is going to be the face whereby there is a moment. So our bending moment at D, let's say D to C, let me name something like that is coming from the C side, or let me name something like D1. Our bending moment at D1 is still at the same point D, but there are going to be two stops there. There are going to be two bending moments there. So now the bending moment at D1 is the bending moment from D without the moment at all. So that bending moment is equal to 28.12 times the distance between here and here. that is 28.12 times 1 plus 1, which is times 2, then minus 20, which is here, times 1. So that is minus 20 times 1. That will be the bending moment from that point. So the bending moment at that point, without D1, we are going to have 28.12 times 2. We have 40, 16. We have something like 50 and 6.24. We have 56.24, then minus 20. So if we do this together, we are going to have it as equals to 36.24 kilonewton meter. So that will be our bending moment at D without the moment right here. So now, having our bending moment at D2, that is, we are going to be including this moment here. But note that because the moment is moving in a clockwise motion, it's going to be negative. If the moment was moving in an anti-clockwise motion, it's going to be positive. So Bm of D2, that will be equals to this bending moment we have 28.12 times 2, we have minus 20 times 1. Then we are also going to remove 30 from here. So minus 30. So at the end of the day, we are going to be having it equals to 56.24 minus 20 minus 30. So if we minus it, it's going to give us 6.24 kilo Newton meter. That will be our bending moment at D2. So now we can look for our bending moment at E. So our bending moment at E here. Our bending moment at E, that will be equals to our bending moment at E, that will be equals to, we have 28.12 times, what is the distance? 1, and 0.5. That is times 2.5. Then we also have our bending minus 20 times 1 and 0.5. 20 times 1.5. We have minus 30. So if we do this together, we have minus 20 times 28.1 times 2. We have 56.24 times divided by half. We have 14.06. So we have 60 plus 70 points. So if we multiply it by this, we have it as 70.3 minus 20 times 1.5. 20 times 1.5 would be equals to 20 times 1.5 would be equals to that would be equal to 30, then minus 30. So we would have something like this, and what you are going to get after adding this up is going to be equals to 10.3 kilonewton meter. That will be the bending moment at E. And the bending moment at A would be equals to 0. If we add everything on up, it should give us 0. But now we shouldn't forget a point. This point this point right here, where x is equals to 0.406. So we have to calculate the maximum bending moment at this curve. There will be a parabolic curve here. We have to calculate the maximum bending moment here. So the bending moment at the max point here, which is the bending moment at the max, would be equals to, we have this one, which is the RB. RB is 28.12 times we have 1 plus 1 2 plus 0.5 2.5 plus the 0.4 meter. It will give us 2.906 for that. Then for here we have minus 20 times 1 times 0.5, we have 1.904 906 meter. Then we also have our bending moment here, which is minus 30. We have our bending moment minus 30, and there will be a small UDL from that distance, which is minus 20 times 0.406 all square divided by 2. So if we sum everything up together and we sum everything up together, we get our bending moment mass are equal to 11.94 kilonewton meter. So at the max of the circle, we have the BM max equals to 11.94 kilonewton meter. So that will be our BM max. Now moving on to our bending moment and our shearing force diagrams, which is the main point of all this. We trace our line down. So now we start with our shearing force. We draw a neutral line straight here. Our shearing force at B is 28.12. So we take it up 28.12, 28.12 kilonewton. Then our shearing force at C here is 8.12. So since this is a point load, it will be a straight line graph. Then we'll take it down to 8.12. Here can be, we have it as 8.12, and this is also a point load. So this is going to go straight all the way to E, because as I said earlier, the moment does not matter in shearing force. It's going to be a straight line directly to E. So now at point E, there will be some changes. From E to E, E is at 8.12 and A will be minus 21.88. So it will end up giving us something like this. There will be 21.88. 21.88 in negative. It will be negative, and this will be positive. This will be positive. So this is our bending moment. Let me write it here. 28.12 is this point right here. So now this is our positive and this is our negative. And the distance between here and here would be, the distance between here and here would be equals to 0.406, which is the distance that we measured here from where x is equals to 0, 0.406. Now to the bending moment diagram, we draw our plane zero line. Now our bending moment at B is 0. Our bending moment at C is 28.12, but this is a point load, so it will be straight line. We have 28.12, 28.12 kilonewton meter. Then also our bending moment at D1, our bending moment at D1 is equal to 36.24. So it will be something like this. Let me take it a little bit. Yeah, something like this. And here will be 36.24. But we also have another point at D2, that is where we included our moment here. So our point at D2 will be 6.24. We take it down to 6.24. This point here is 6.24. And then from here to here, from here to here, we have our bending moment at E, bending moment at E, our bending moment at E here should be equal to 10.3. That means it is not actually a straight line from here to here. It is a parabolic curve due to the influence of the UDL that is on the left side. So we are going to have a parabolic curve. We are going to be having parabolic curve, like a 2-degree line in somewhere here, is it not too high like this? From here, we are going to be having a curve. But this point E here, this point E that we measured from point E here, this is the one that is 10.3 kilonewton meter. But according to our calculation, we have a maximum point at 11.94 meter. So there will be a point right here that will be 11.94 kilonewton meter. That is a point, the maximum point on the curve. And then we also have our bending moment at A to be equal to 0. So this is the shear force diagram and the bending moment diagram. So that is it for adding a moment on the simply supported beam.